Okay, here's another fluid statics problem, and in this case we have a crown and we want to figure out what percentage of gold was in the crown. This was a famous experiment done by Archimedes back in the day, and in order to find out how pure the crown was made, whether it was made from pure gold or an alloy of gold and silver. And of course they did find it was made from an alloy of gold and silver. So we're going to calculate this, and you see they give us the density of gold, density of silver, and so we're just saying if the weight of the crown is 1,000 grams in air and 940 in pure water, so now calculate percentage of gold. So for this type of problem, what we need to know is that buoyancy is an upward force, acts on all objects that are partially or completely submerged in a fluid, and the fluid can be a liquid or a gas. In this case, it's water, so it's a liquid. And we're going to use Archimedes' principle, which states that the buoyant force on a submerged object is equal to the weight of the displaced fluid. Okay, so as you can see, I've drawn out two different cases for this crown. So this red ball represents the crown, and it's submerged in the water. And as you can see, the volume from buoyancy will be the same. This is the volume of buoyancy, will be the same of the volume of the weight. But in this case, since it's only partially submerged, we only have half of the volume of the weight. So V, volume of buoyancy, would not equal volume of the weight. And so then you can cancel out the volumes, which we'll get to. But in this case, we actually have VB equals VW, so we can just say V and V, so just neglect the little subscripts. Okay, so now that we have that all sorted out, we can begin to try to solve this. So since we said the buoyant force on a submerged object is equal to the weight of the displaced fluid, we can set this up as a ratio. So W, which is weight over force of buoyancy, and rho crown GV, rho water GV, so the G and V's cancel, and you're just left with rho crown over rho water, which is the same as specific gravity of the crown. And if you recall, specific gravity of crown, remember from earlier videos, the density of the crown would be specific gravity times density of water. So you just rearrange that and find specific gravity. Okay, moving on. So we can also say, instead of force of buoyancy equals density of water GV, we can say force of buoyancy equals the weight of the crown in air minus the weight of crown in water. And that gives us the weight of displaced fluid, as we said here in the definition. So once we have that, we can actually use this ratio again, weight of the crown in air over force of buoyancy. So W is weight of crown in air, and we have weight of crown in air minus weight of crown in water. And that, of course, again gives us specific gravity of crown. And so it's important to use this equation here instead of rho GV, because we do know the mass of the crown in pure water right here. So that's what we do now. So we can break weight into components of mass and gravity, as you can see there, and all the gravities cancel because it's constant. And so we have 1,000, as it says in the problem here, 1,000 in air, 1,000 minus 940 in water. And so we get our specific gravity of the crown as 16.67. Okay, so now we want to find the fractional volume of silver. So how we're going to do that is we're going to use an equation using our specific gravity, and we're going to assume the total volume of the crown is 1 centimeter cubed, just for easier arithmetic. And we're going to say in that volume of 1 centimeter cubed, we have 16.67 grams per centimeter cubed of density. That will be the density of the crown. And we're going to now break this density and volume up into its separate gold and silver components. So for the gold volume, we're going to take 1 minus x, and as you see, we've denoted x as the volume of silver. So, and then we multiply it by the density of gold. So that's the gold portion, and then for the silver portion, again, x is the volume of silver, and then this is the density of silver. So once we simplify this, 1 times 19.3 is just 19.3, and then minus x times 19.3 is minus 19.3x, and so we can combine this minus 19.3x with the plus 10.5x, and we get 8.8x, and the 19.3 stays the same. This one here had a centimeters cubed attached to it, because as we said, we're assuming the total volume to be 1 centimeter cubed. And now we get a solution of 0.2989 centimeters cubed, and that is for silver, as it's highlighted in the silver color. From there, now we can find the volume of gold in the assumed 1 centimeter cube volume, total volume. So all we have to do is take that total volume and subtract it from the partial volume that we found for gold, silver, and now we find the partial volume of the gold to be 0.7 centimeters cubed. And from there, it is fairly simple to find the mass of gold. All you have to do is use this formula, mass equals rho v. And so our density of gold is 19.3. And then we just found our volume to be 0.7, and so our mass is 13.53 grams. From there, all we have to do is find the percentage of gold, and we'll have our final solution. So all you have to do there is take our mass and divide it by the mass of the total volume. So this is the mass of the gold minus the, mass of the gold divided by the mass of the total volume. And that gives our percentage of 81.2%.